Okay. I am going to tell you how, in the context we've been talking about, you can think about machine learning. And I'm going to tell you my physicist's view of what is done in machine learning and the data assimilation view of providing tools to help understand what is accomplished by machine learning. In machine learning, if I go to this picture from data assimilation of starting at some time and moving along to another time, in machine learning, in the simplest possible cases, you can make these much more complicated. What you have is a device with layers in the device. I'll show you a picture of it. It goes by the name of a multi-layer perceptron. And you have inputs that you've measured, and you have outputs that you want the machine to learn about. That's your data set. Very exciting data set that was published about a year ago. Took 128,000 pictures of your retina taken in the office of your eye doctor, not your eye doctor, but somebody's eye doctor, that were classified as being an indication of healthy eyes or diseased eyes by practicing physicians. And so the input is 128,000 images, and the output is healthy, diseased, healthy, diseased, diseased. The machine doesn't say, if you're healthy, congratulations, lead a good life. And it doesn't say, if you're unhealthy, go back and see the doctor. It just tells you 0 or 1, yes or no. The machine took a long time to train. I'll tell you what the structure was. It was extremely expensive because it took 3 practicing physicians each to analyze the 128,000 pictures and agree on them. And that costs a lot of money for the physicians. And so the institution that did this was Google, and I hear that they can afford it. So here's a picture and the language of that kind of machine. You have an input, they're in squares, and I tell you the image. How do I tell you the image? I represent the image by n pixels, and that's my image. So I have n squared inputs here that represent the picture. I have what are called hidden layers. For us, in our language, that represents times at which you're not making a measurement. And you have a structure that you make up. I'll show you what the general structure is. And you have an output, which is, pardon me?
Sorry for interrupting. Looks like a neural, artificial neural network. Not sure.
It is. It's a multi-layer perceptron. Didn't I say that?
Yeah.
All right.
Sorry.
All right. I hate the word artificial neural network because these are called neurons, and these bear no resemblance whatsoever to what walks into Dan's lab.
So what are the weights for different?
Let's look at the next. All right. This is just the graphical architecture. And in the case of the images, as I said, capital N there is 100 n squared by n squared, whatever that was in the resolution of the picture. And this was healthy, diseased. You need a rule that takes your input at that input location and moves it through these layers. And it's long been known that the operation on the input information has to be nonlinear, step by step, in order to get a device, a machine that recognizes something, that learns something. So in our little picture, it looks like this. We have an input location, an output location, and intermediate locations, which go by this fancy name of hidden layers, in which you move the information around. There's a standardized format for it, which I think is can be improved on, but the one that's used I'll show in the next rule. So here's what the machine learning operation does, in fact. There is data, it's the picture of your eyeballs, at layer 0, and there is healthy or diseased at the final layer. There are little active units called neurons at every layer. I showed you a picture of the layers. And there's a rule that tells you how to take the activity at some layer, operate with it by a nonlinear function, which is more or less up to you, but is chosen typically to be more or less sigmoid, because the people who initiated this thought that's what neurons did, added up things. And there's a weight that is up to you, which are the parameters of your network that tell you how neuron I in layer L is connected up to layer, in layer L to neuron J, and that tells you the activity at layer L plus 1. This is the measurement error. This is a deterministic model. If you don't like the rule for the model, make another model. But this is, I'm trying to give you a flavor of what is actually done instead of criticizing how it is that they do it. What I want to do is bring this set of questions to a statistical physics problem of the kind that we just discussed. The first thing I think one needs to do is to recognize that this equality is an approximation because we don't know what the model is. We don't know what the correct layer-to-layer rule is. So let's recognize that this shouldn't be an equality, but there should be model errors as well. If you add those model errors to a cost function that represents the input at 2 points only, that's what's done in machine learning, input layer and output layer, and you add this as an additional term here into the cost function, which I've been calling an action, you get the standard model. If you interpret the layer label as time, this is exactly discrete time data assimilation, where information is entered at one layer and outputted at another layer. The total probability is e to the minus action. And we want to calculate, and I passed over that slide, exactly the same integral as before. So we want to take that action, which is composed of inputs with model errors and outputs with measurement errors, and a model of how to move through the network, which we make inaccurate instead of precisely deterministic. Now, somebody asked me, should ask me at this point to say the word Tikhonov regularization. I think that's you. Okay. This is Tikhonov regularization in the following sense. The minimization of the measurement error is at 2 locations and in a subspace of all the degrees of freedom that are in the model. And the goal is to determine all of those weights, W of L, and that determines the architecture of your model, which you have trained to recognize eyeballs, or retinas, I'm sorry. The model is exact when RF goes to infinity. And so you know what to do, right? You study the problem when RF equals 0. That gives you the global minimum of that problem, which is degenerate. You start turning on RF a little bit at a time. That regularizes the search in this subspace by bringing in all of the variables, the x's which are the activities at every layer for every one of the little active units they call neurons. And you do the minimization over W and over the X's as a function of RF. I'll show you the result of that in an example. All right, here's the example. This is what I would call, in the language that we use here, a twin experiment. I generated data. Now, I could have just come in to you and say, I generated input pairs, inputs, and outputs, and I made 10,000 inputs and 10,000 outputs. Here's my data. You make a machine of this form that tells me, when I give you an input, with high accuracy what the output is. That's the job of this machine. Here's the machine we used to actually generate the data. We took one of these networks with one input layer, one output layer, and 98 intermediate layers. 98 isn't an obvious number, but 98 plus 2 is something you might think about. We put in some inputs. We chose the weights in this machine from random numbers, but we had a definite machine. We have a definite operation on inputs and outputs. And then we put in 10-dimensional inputs and took out 10-dimensional outputs. And we added noise to them and put that in our library for our noisy inputs and outputs. And now we said, build a machine that recognizes those data sets. Noisy inputs, noisy outputs of a certain structure. Completely up to us, but we were told we have to build the machine that has this structure, but we weren't told how many layers we have. We weren't told what the noise levels were. But since we knew what they were, we wrote an action of this form. And we solved the problem just because, well, this isn't the only solution we looked at. If you have 50 layers, remember the original generation of the data had 100 layers, but we didn't know that. We have 50 layers, and capital M is the number of input-output pairs we took out of the library to train the machine. Train the machine on one example here, 2 examples, and 10 examples. Oh. Okay. All right, look at this. This says that when you train the machine with one example, look at the number of local minima. There are a lot of them. Laplace says none of these is really dominant, so add them all up. In the machine learning world, they have no idea that the structure of the action looks like this. They just say, we did our job. It's one of these minima. We'll take it, and we hope it predicts well. That's nice. Suppose you gave it 2 pieces of information. Well, it changes into that green set of minima. If you blow it up, you'll see there's just one minimum there. I mean, the pixel size is too big on this picture. And if you give it 10 pieces of data, pairs of data, it looks like the red thing. Now, if you had your choice, you'd probably choose this one or that one and not this one. And this is a tool completely absent in the machine learning world, as far as I know, that is totally taken over from the analysis of data assimilation in the cases that we've been talking about, that says, don't do this. But do this, and your machines will work better. There is an example. Now, the numbers here are going to show you how good the predictions are as a function of these numbers. But the numbers here aren't important. What's important is that the structure of the surface over which you're searching as in the case of data assimilation for transistors or neurons or whatever, simplifies as you add more measurements. If this happens to be the structure of the surface, what I'm about to tell you is not a proven thing, but a conjecture. There's a phenomenon known in the machine learning world as adversarial perturbations. That's a very fancy name for the following. You choose one of these paths and the, action levels in the path associated with it, and that's your machine. And now you come along and perturb your data a little bit, and your machine no longer works. Seems to me that what happened is you bumped yourself to a different path, because these things are very, very close, and it means that your surface you're searching on is full of all these local minima, and you bumped into the wrong one. Up here, if you trained your machine on that number of data, there's only one path. There's only one minimum, and a small perturbation should be robust. I haven't proven that, but I think that's the kind of question you can ask in these machines. There's something that IBM will advertise that it will sell to you at a price I leave you to negotiate, called deep learning. Deep learning is associated partly with good data sets. I'll have a word to say about data sets. And machines of many, many, many layers. How many? So what's a good data set? Well, the eyeball data set is an example of a good data set. It's lots of examples of pictures of eyeballs, curated by professional ophthalmologists so that it has a lot of information in it. It's not just the number of examples in your data set. I could give you 10 to the 23rd examples in your data set, all of which were the same, none of which would give you information about the machine except the first one, because they're all the same. So you really need to capture variation in your signal in order to get a good machine.